All right, well, welcome everybody to season 2 of the Australian Geometric PDE seminar. You get the benefit of a little preview of a brand new website behind me. It's a brave new world. We have all sorts of amazing things happening. But today we're going to start off with these notes here. So we're going to work through lecture notes by Al Son, who was attending a course of Richard Baumler's, and there's some really good stuff on Ricci flow there. We get some classic stuff like Hamilton's original result quite quickly, and then we've got some new modern developments and so on. So it should be a lot of fun. But today we're going to start off with some background differential geometry, just to get everybody up to speed before we start in the Ricci flow proper. So James Stanfield is going to start us off with that. So I guess without further ado, let's turn over to James.
All right, thanks, Paul. Thanks everyone for coming, and thanks again for the invitation to speak. So let me just share my screen. So as Paul said, we're going to start with a nice, gentle introduction to Riemannian geometry. So I guess the goal of the next 2 talks is to understand the Ricci flow equation, right? So to understand what the heck's going on here. This talk, I'm not going to get into a crazy amount of detail. I think we'll probably cover the left-hand side. This is talk 1. And then next time, we're going to talk about curvature. This is talk 2. Hopefully everyone understands that bit. And then we'll see how we go. So yeah, again, this is going to be very gentle. I apologize to the experts who know what's happening. But if people feel I'm skipping over important details or anyone has questions, please feel free to interrupt me or say in the chat. So yeah, I'll just jump right into it and we'll see if we can understand what's going on here. Okay. So first up, let's talk about what Riemannian geometry is. But before we do that, I guess we have to understand a little bit of what's going on behind the scenes. So let's let M be a smooth manifold. And I'll just make sure people can see what I'm writing. Yep, okay, good. So I mean, generalization of regular surfaces. If you don't know what it is, it probably suffices to think of a regular surface. So yeah, and then we'll let Tm denote the tangent bundle. So what is this? This is the disjoint union of all the tangent spaces. Be its tangent bundle. Okay. So what are the tangent spaces? So very rapid introduction to what these things are. These are linear maps from the smooth functions into R such that they act as derivations. So this is equal to x of f, g of x, plus f of x, capital X, g. Okay, and so we just think of this as sort of differential operators at the point. So in local coordinates, sort of xi denoted by phi of x, say in a chart, right? So some open subset of x with a coordinate chart. There is a basis, so I'll say these operators are a basis for this vector space Txn. Okay, so what are these things? Well, they act on a function just by differentiating in the ith component of the function represented in coordinates. Okay, right. And maybe I'll just, for completeness, I'll dualize this concept. So we'll just let T star M which is the disjoint union of the dual spaces, be the cotangent bundle. By the way, if you can't read anything I'm writing, again, speak up and let me know, because I understand my handwriting can be a bit funky. And then this has basis. Suppose we don't need a full stop here. With basis dxi. Right, and that's just the dual basis of our original basis. I'm going to be pretty liberal about forgetting at which point these things are acting, because again, we just think of them as vector fields or one forms. In saying that, let's let this be, if you like this notation, be the vector space of, well, I'll just say denote the vector fields. I guess the smooth vector fields. On M, right? And so these are just maps from M to Tm such that we always lie in the right tangent space, okay? And then I guess the dual concept, right? So we'll just let be the one forms on M. So these are just the co-vector fields, defined very similarly. I guess if we want to use this notation again, these are sections of the cotangent bundle. Okay, so I guess if you've never seen this before, we have some smooth manifold M. And then at each point, we have the tangent space, which we just think of as a vector space lying over M. And then we have a bunch of vectors, which again, we think of as differential operators acting on smooth functions. And then a vector field is just at each point, we assign some vector in the corresponding tangent space. Okay. So now we know what vector fields are. We can define the most important object that we need, which is a Riemannian metric. Okay. So a Riemannian metric on M is a smooth assignment. Okay, I'll maybe flesh out what that means in a second. We take a point X in the manifold and we send it to some map of tangent spaces, some linear map. Of inner products to each tangent space. So what does that mean, right? If we don't remember what an inner product is, it's symmetric and it's positive definite. So this is greater than or equal to 0. And equality holds if and only if x equals 0. And this is for all x and y in our tangent space. Okay, so what do I mean by smooth? Well, you could think of this as a section of a tensor bundle and talk about smoothness that way, or if you don't want to worry about that yet, we can just say that the map sending x to gx, xx, yx is smooth for all vector fields x and y. Okay, so we have sort of a smooth assignment of inner products. So we have a notion of lengths and angles assigned to each tangent space. And this is how, I mean, this is the essence of what we want to do, right? We want to talk geometrically about things, and this is a pretty natural geometric object. Okay, I guess G is a tensor field or a true tensor field, for those who know what that is. Okay, right, so in coordinates, say xi in a chart So we often want to talk about these things locally, so we want to write them in coordinates. So we can write G as just being Gij dxi tensor dxj, or equivalently Gij dxi tensor dxj. I should say, for the record, that repeated indices are always summed, at least for this talk. So there is an implicit summation going on here over I and j. I've just written the same thing twice. What I meant to do was get rid of that. Okay, and then, well, what are these quantities? Well, Gij is just G acting on our basis elements. And dxi, dxj is just the symmetrization of this tensor product. So, I mean, we want G to act on vector fields. So what do? We kind of just let this act on two vector fields. And then the tensor product means that this is acted on by that one, and then this is acted on by that one. Okay. So what do we have? So, I mean, I guess if we want to be completely detailed, my dog's saying hi, we can write this. So we can expand, sorry, that's Yj. We can expand any two vector fields in this basis, and then what does G look like when we act on them? This is just the sum over I and j of xi yj, sorry, gij. Okay, so this gives us a coordinate representation of this inner product, or Riemannian metric. And so this is just for later. We're going to denote by Gij the entries of the inverse of the matrix corresponding to all these entries. Okay, so the entries of that. Cool, and so what does this mean? Well, this means, I guess if you like computing in indices, that if I sum over this J here and I multiply these two together, well, this is just giving me the components of the identity map by definition of the inverse, which is just this Kronecker delta, right? So there's 1 when they're equal and 0 when they're not. All right. I'm going to try and just do as many examples as I can so that those who don't know what's going on can hopefully piece it together. Before I do, I'll ask if there's any questions so far. There's a lot happening in the chat. I'm sorry for not seeing this.
Hey, James, it's all good.
Yeah. Okay.
We were just chatting about the approach to tangent spaces. So I don't know if you want to comment on if, say, you have a curve on your manifold and you look at the derivative of that curve, it's in, you know, how do you connect that with this one? Maybe.
Yeah, that's a good point. So if I've got a curve, I guess I can show one direction, the other direction is not as easy, right? If I have a curve mapping from some open set into my manifold, right? This induces a so-called tangent vector, right? In the following way, so I guess I'll call it x sub gamma, and this acts on functions as follows. So I guess we want this curve to meet, so to begin at x. And this would be, what would this be? F after phi. So phi maps from the manifold. So I guess it would be this. Sorry, that's not phi, that's gamma. Okay, so we just look at, so this curve induces a vector or a differential operator which acts on functions just by taking the derivative of the composition of that curve. Okay, so I guess the equivalent way, oops. I mean, the corresponding way to think about this is if we take the directional derivative.
So excuse me, James. If you've got gamma going into M and F is just a function from M into the real numbers. I don't think you need that coordinate chart there.
Correct. Sorry about that. Yeah. I was getting my definitions mixed up. Right. Okay. So this is even better, right? So if we take the directional derivative, so this is everything's in Rn right now. So we take x some vector and f mapping from Rn into say R, right? Then the directional derivative is just, well, one way to do it is just take the derivative. Well, we just compose f with gamma, okay, where gamma dash of 0 is going to be x, right? And maybe gamma of 0 equals x, and we want to take the derivative at some point. Okay, so that's I guess maybe this kind of convinces you that these definitions are equivalent. Of obviously, given a curve, I can give you a derivation. Given a derivation to give you a curve is a little bit more tricky, but not too hard. So hopefully that clarifies some intuition there for people. All right, cool. That was a good question.
For me. It's all good for me.
Cool. Good. All right. So maybe we should do some examples of Riemannian metrics. The first, most obvious example is just Rn. So in this case, the tangent space can actually just be canonically identified with Rn itself. And we'll just take the metric to just be what I'll call the Euclidean metric, which is just literally just the standard inner product on Rn. Okay, so what does that mean? If I take two vectors, this is just xi, yj, delta ij. Okay, i.e., we just get this in coordinates. Okay, so this is the, I guess, the most basic metric you can think of, the one on Rn. And I guess if we want to just write this in the other notation, this is dxi dxj times delta ij, which is just the sum over I of dxi squared. So this is like your line element in Rn. Okay, so that's where basically all the g's are the same because we can canonically identify all the tangent space, all the tangent spaces. What about a little bit more of an interesting one? Let's take m equal to the sphere, which sits inside, well, the n-dimensional sphere, which sits inside n+1 dimensional space. So for x in R, for x in Sn, we can write the tangent space of the ambient space as just being the tangent space of Sn plus the line spanned by the point itself. Okay, so we want to draw a little picture. We have the point in here. We have the tangent space. I guess this is for n equals 2. And then x is this vector. And we've got this line spanned by x. And then I guess the tangent space of the sphere is the complement, or is a complement of that line sitting in Rn+1. Okay, so we can define the sort of the round metric. Try and keep this chat open. This doesn't the round metric as just being the standard Euclidean metric on the higher dimensional space restricted to the sphere. This generalizes, by the way. If we have any embedded submanifold in a Riemannian manifold, you can just look at the tangent space sitting inside the higher tangent space and just restrict the Riemannian metric to induce it. I suppose to be absolutely correct here, I should evaluate these metrics at the point x in my sphere. Okay, but it's the same metric, just restricted to the tangent space of the sphere. But even in doing that, we're going to see that we're going to get some like local invariance appearing later on, but we won't talk about that until next week. Final example. Let's take n-1 copies of R and add on a copy of the positive reals. And I'm going to call this Hn. Okay, and then I'm going to call the hyperbolic metric. That's just going to be the Euclidean metric divided by the last coordinate squared. Okay, so this is the Riemannian metric for hyperbolic space. This is a space of constant negative sectional curvature, which we'll properly define next time. And I guess if you want to figure out the coordinates of these, it's just delta ij divided by xm squared. All right. So they're three very important examples, but fairly straightforward. We can also construct Riemannian manifolds out of other ones. So let's take two Riemannian manifolds. And then what is the tangent space? So I guess we want to consider the product M1 cross M2. Okay, well, the tangent space of the product at some xy can be canonically identified with the direct sum. And then the metric is, and I'm sure you can pretty much guess what this is going to be, is just the one that makes this an orthogonal decomposition. So namely, this is gx of x1, y1 plus gx x2, y2. Okay, so this is for x1, well, xi, yi in t, x, m, tm. Fine. Okay, so that's good. And then maybe just for completeness. So
I
this
think
is
you want like a G1 on the first one and then a G2 on the second one, right?
Yes, correct.
Yeah, all good.
So G1 x and G2 x, correct. Okay.
Y, I guess.
Yes. Probably should have called it x1 and x2, but that's all right. So this is an embedded. So if I take an embedded submanifold. Okay, so again, the tangent bundle of this one is just sitting inside naturally the tangent bundle of the other one. And so we can induce a Riemannian metric by just restricting it to that. Okay, and this allows us to construct a whole bunch of manifolds. I'm going to construct one more example, but first I'm going to take an interlude and look at some geometric stuff, because it will be important when we dive into looking at the Ricci flow to see how these objects evolve. So actually, maybe I'll stop real quick and see if there's questions. All right, cool. So geometric stuff. Let's let gamma be some, I guess, piecewise smooth curve. Piecewise smooth curve, and then we can define the length. The length of this curve is just defined as follows. It's the integral of the norm of its velocity over time. So what do I mean by the norm here? This is just the one induced by our inner product. But again, we're changing the point in time. So we're changing our inner product, but in a smooth way. So we do this computation. Okay, and that gives us the length. And this induces for us a metric, a classical metric, not a Riemannian metric, right? So we can find the distance between 2 points as just by taking the infimum over curves, mapping into M, where we start at X and we end at Y, and we just take the length. Okay, so the infimum of these lengths gives us a classical metric or distance function. Okay. And I'll just say, I'll just define this. So we say G is complete if it's induced, the metric space induced by its distance function is complete. Okay, and the corresponding Riemannian manifold is called complete as well. And there's a beautiful theory behind that, which I'm going to sweep under the rug in the interest of time. Yeah, so more geometric stuff, right? So if M is in fact orientable, G induces a volume form. Okay, so in coordinates, we can define this quite easily. I'm going to define it like this: dg. This is how Bamler uses it in his notes. This is square root of the determinant of this matrix representation of G, and we do this wedge product. Okay, so that means if f is some compactly supported function, then we can define the integral. We can talk reasonably about the integral of f over m. So canonically, on say just a differentiable manifold, this is not possible to talk about something like this, but the Riemannian structure gives us a natural volume form to which we can integrate functions over, right? So if, I guess, how do we compute this integral, right? Well, if the support of f is just contained in some coordinate patch, right, then the integral of f is just given by the integral over Rn of the square root of the determinant of Gij times f dx1 dxn. Okay, so it just turns into your usual integral. And then if m is compact, then we can define a volume. So this just being the integral of the volume form itself. Okay. Right. Maybe as a real quick example of this volume form, just to bring it down to earth, if M is, say, let's say the sphere of radius R, okay, then the round metric, which I didn't define before, but you can write in local coordinates as in coordinate, spherical coordinates as follows. Okay, and then the matrix representation of this, so I guess this is G. This is just R squared 0, 0, R squared sine squared theta. And so what does that give us? The volume form is just the square root of the determinant times d theta d phi. So there's R squared sine theta. So this should be familiar from undergraduate vector calculus courses, hopefully. All right. Another important definition. So in isometry, so let's let M I G I be Riemannian manifolds as well. Okay, so an isometry is a diffeomorphism. Okay, this just takes M1 to M2 such that G1 is the pullback of G2. And what does that mean? I haven't defined what that is. If you like, G1 of XY is just G2 of the differential of F applied to X and the differential of F applied to Y. Okay, so this is for X, Y in the vector fields. So this is a lovely concept. I've got, might be worth noting. Oh yes, that's a good point. Yeah, maybe strictly speaking, you don't need orientable here, but to get the existence of a non-vanishing top form, you do. And then there's some technical things you can do with orientable covers and things, right? So to get around that, but I wouldn't say I've prepared enough to say too much on that.
Yeah, it's all good. I was just making it. Yeah, it's all good. Yeah. I just thought maybe it's worth noting for people who are watching it and might think that we're implying that it's not possible. It's just more convenient when it's orientable.
Yeah, absolutely. It's a good point. I should have noted that. Yeah, thank you.
Okay, it's all good.
If support of F is not in chart partitions of unity, yeah, I think that would that's how you would do it. Yes. I think, yeah. So where was I up to? Okay, so I was talking about isometries, right? So this is the natural equivalent of Riemannian manifolds. This is a map that will, by nature, preserve lengths and angles. Okay, so a very important class of maps. This group, right? So we just call, we'll just define this as, well, I'm just going to define this ISO-MG as isometries mapping from M to itself. Okay, and this is a group under composition. So maybe just like two examples, right? The isometries of just Rn with the Euclidean metric are what? Well, this is what we call E of n, the Euclidean group, which is just Rn semi-direct product with O of n. Okay, what do I mean by semi-direct product? I just take the usual product of a group, right? So I take some vector in Rn, and I take some A in On. So these are the orthogonal matrices, and they act on some X by AX plus B. Okay, so this is the rotations and reflections, which comes from the On factor, and translations, right? So we can shift Rn and it preserves the Euclidean metric, okay? So this is all the isometries of Rn. The isometries of Sn, well, they all come from isometries of Rn plus 1. Remember, Sn sits inside Rn plus 1, okay? But I can't shift things anymore, right? Because I'm on the sphere. I have to maintain a constant norm. So this is just On plus 1. So they're the isometries of the sphere. Reflections and rotations.
Sorry, James, do you mind going back one slide or one page up? Mm-hmm. When you say that an isometry preserves the metric, I'm not sure I can see it from that formula. Can you just go through it explicitly?
I mean that, so I guess preserving the metric might be wrong. These are two different metrics, right? Because they're on two different manifolds. But the isometry means that we can completely relate them, right? So I guess F being a diffeomorphism means that dF, mapping is from the tangent spaces, is a linear isomorphism, right? So I get this identification of tangent spaces. And then it turns out that this identification, if I consider now these two vector spaces as Euclidean vector spaces, right? So like this and Txm2 G2 of X. Then this, now this is just linear algebra now. There's no talk of functions on manifolds. As an inner product space, this becomes an isometry of inner product spaces, right? Does that make sense? So we call F an isometry if its differential is an isometry of all the inner product spaces on the manifold. Does that clarify things, or?
Yeah, sort of. And the question is whether these isometries always exist. Is that?
Well, you always have, for example, the identity on on a Riemannian manifold, right?
But the image manifold can have a different metric, right? I mean, G1 and G2 are different metrics, and you're trying to relate them through the diffeomorphism. Is it clear that you can always do that?
Oh, right. No, of course. You can have two different Riemannian manifolds, and there may not be an isometry between them. Okay. Next week, we're going to talk about invariance, local invariance, which proves that this can't happen. So there are certain quantities, namely the curvature, which are preserved by isometry. So the curvature, which is preserved by isometry, but if we have two manifolds with different curvature, then there can't possibly be an isometry between them, right? So good point. Yeah, so two different manifolds could have no isometry. Cool. Thanks for that question. That was very important. So what was I saying? Right, so I was talking about isometries of the sphere, and now here's one of my favorite theorems, commonly called the Myers-Steenrod theorem. I'm going to highlight it because it's very nice. So if MG is connected and complete, so not too crazy assumptions, then the isometry group is a Lie group. So meaning not only does it have a group structure, it's also a finite dimensional smooth manifold with compatible group structure. Okay, and that opens up a lot of theory for us. Namely, this is going to be my sort of last example of how to construct new Riemannian manifolds. So let's let MG be as above, namely connected and complete. And G be a Lie subgroup, or I'll say closed Lie subgroup, because that's important. Closed Lie subgroup acting freely on M. So what do I mean by that? I mean that if any point is fixed by some f in G, then this means that f is the identity on M. Okay, and this is for all E in M, and I guess F in G. So we take this closed subgroup of isometries, and we ask that the only isometry that fixes points is the identity. Okay, then the quotient, right, which is just kind of the orbit space. So this is, by this I mean every f in G applied to the point P such that P is in M. Okay, so the set of all orbits is a smooth manifold with Riemannian metric G tilde such that the projection, or sorry, the quotient map is a local isometry. I haven't defined what local isometry means, but it just means if I restrict to a small enough neighborhood, then I'm a diffeomorphism onto the image, and this smaller map is an isometry, right? So
I have another question, James. Sorry.
Yes, of course.
Couldn't you allow for diffeomorphism that say have discrete, like reversing points and things? That would still count as isometry, wouldn't it? What I'm failing to see is the notion of smoothness of the isometry group. In other words, is it clear that this group is connected to the identity?
So you're asking if I think the isometry group can be discrete, if you're asking, maybe. Please someone jump in if I'm wrong.
Well, I'm just asking whether the group of isometries has always a or you just restrict to the connected component to the identity?
A Lie group can have different connected components, right? So the claim is that if you want that the connected component is a connected Lie group, yes, and then it has only countably many connected components.
For example, if your isometry group happens to be Z2, it is possible to have Riemannian manifolds with isometry group Z2 that sort of trivially counts as a Lie group because there's not really much smooth structure to check there. It's a zero-dimensional Lie group, I guess, is what you could say.
So James, perhaps some examples would help here to get an idea of, like, for instance, having a torus, right? Say the embedded torus in R3, just that, right? Then you can see that there's a continuous set of isometries, right? And then you've got other isometries which do not belong to this like rotational group of isometries. Say, for instance, like flipping it upside down, which is clearly another isometry. That will be like different connected components.
Yeah, that's a good point. So yeah, you can rotate that way. And then, yeah, you can sort of flip it upside down. You can reflect it in a bunch of different axes. And yeah, as you said, that gives you different connected components of the isometry group. Right. Any more comments or questions before I? All right, cool. So I guess this is kind of important to emphasize, right? So we can construct new manifolds via the action of the Lie group. Okay. So I guess I had an example in mind. Maybe it's too simple to satisfy most people, but that's okay. So let's let M equal Rn again. Okay. And then we'll just take Zn inside the isometries of Rn. Okay, and so what do I mean by that, right? So Zn, I guess for every n, I associate a function or an action that just takes some x to x plus n. Okay, so I just translate it by some integer or some integer vector, right? So this is in Rn, this is in Zn. I guess maybe to be absolutely clear, to each n, I can sort of associate an isometry f sub n which acts as the following. Fn of x just gives me x plus n. Okay. Now, it turns out that Zn acts freely. Okay, the only way I can fix a point is to have n equal to 0, i.e. the identity of that group. And so that means that Rn mod Zn is naturally a Riemannian manifold. Okay, and people might recognize this as being the n torus, which is just n copies of S1. Okay, so it'll turn out that when I define it properly next week, that all flat manifolds, meaning manifolds with vanishing Riemann curvature, are actually quotients of this Rn. Okay, so this is why I wanted to point out this construction. All right, so we started 5 minutes in, right? So I guess I still have a few minutes. What I'll do is I'll talk a little bit about where we're going with the Levi-Civita connection. The problems that we have trying to generalize differentiation, and then maybe I'll talk about it properly next week, so I have some more time. So I guess this section is called the Levi-Civita connection, which is really the heart of Riemannian geometry. What is the metric on mg? Oh, good point. So you can choose coordinates naturally on the torus just by choosing them on the sphere, right? So the coordinates are x1 up to xn. And then the metric is just dxi, dxj. It's the same, it's written the same as the Euclidean metric because the quotient is a local isometry. Okay. Hopefully that helps. So I'm just going to mention the Levi-Civita connection, but probably not talk about it too much. So what we want, right? So we want, I mean, what have I written? So let's take a vector field Y. Okay, and so we want the sort of some notion of the directional derivative of Y in the direction, say X, some fixed vector. Okay, so we have this manifold M. Okay, and then maybe Y is this vector field. Okay, and then maybe at some point we have some X, and we kind of want to just differentiate Y in the direction X. Okay, in Rn we do this component wise, and it's quite easy. So how do we do it in Rn? Well, we do the following, right? So we take we define the directional derivative in the direction X of Y is just the usual derivative of Y composed with some function. And we evaluate that at t equals 0, where gamma of 0 is just X, where we want to take the directional derivative, and gamma, the derivative at 0, is equal to X. Okay, but this derivative is simply Y, so it's like some limit, right? As t goes to 0, of Y of gamma of t minus Y of gamma of 0, which is just X, over t. And so you can see where our problem comes in if we try to directly generalize this, right? We're subtracting off, we're subtracting two vectors, okay? So here, we have txm, okay? And then maybe over here, this is some other vector space. This is t gamma of tm, okay? But a priori, so remember in Rn, we can canonically identify every tangent space with Rn itself, okay? And so we immediately get a very natural interpretation of what that minus has to be. It has to just be subtraction on Rn. But of course, what does it mean for Y of gamma of t to be subtracted from, to be subtracted from Y of X, right? There's no clear way to do that on a general manifold because we don't have an identification of vector spaces. And so basically what we do is we impose an identification of vector spaces. And that's what leads us to the definition of a connection, which I'm not going to do. But I will note a couple of things about this directional derivative that we might want to take with us when we generalize it. Okay, so first of all, if I take the directional derivative of the inner product of two vector fields, then by just the product rule, this is the directional derivative. Sorry, this should be kind of yz in here. Okay, so maybe just to clear, this is yz in the vector fields of Rn. Okay, so this is yz plus y t sub x z. So that's one thing we might want to take with us when we generalize this thing. Another thing is the following. If I take the directional derivative in this direction of, say, this vector, okay, so remember these are Rn, so you can identify them with just the coordinate, the standard basis of Rn, right? Then this shouldn't matter what order I do it, right? So this should be d by dxj, d by dxi, i.e. we should have kind of this property holding. Meaning we want, when we define it, we'll want our connection to be what we call torsion-free. So we want it to be so-called torsion-free, and we'll want it to also be compatible with our Riemannian metric. And it turns out, and I guess I'm spoiling it, that there's a unique way to do this, which is basically the basis of all Riemannian geometry. Hence, they call it the fundamental theorem of Riemannian geometry. So I'll probably leave it there. If anyone's got any questions, let me know. But the roadmap for next time is obviously now to understand the right-hand side of the Ricci flow equation. Namely, we're going to introduce curvature and we're going to compute some examples and have some fun with that. All right, well, thanks for listening. Let me know if you've got questions.
Thanks for that, James.
That's all right.
Thank you, James. That was awesome.
Yeah, excellent stuff. Thanks. Yeah.
Got any questions for James? Here we go. There's one. Willem asks, Willem, you can actually ask yourself if you like, but otherwise James can read it. I mean, it's in the chat.
Yeah. How do you in general give a metric to M mod G? That's a good question. Well, first, you have to construct a smooth manifold structure, right? You have to figure out what the heck the tangent space is. And you can do that in the process of proving that it is a smooth manifold. I think there's like canonical coordinate charts you can get. But in general, I guess you've got this this quotient map, right? And then I guess the metric is literally defined as the one that makes this a local isometry. Okay, so I guess d pi maps from the tangent space of M to the tangent space of M mod G. Okay, and then you just want, I guess, G of xy to be, so I guess we've got a metric here, G, and we've got a metric, induced metric, G tilde. You want this thing to be a local isometry, so you can define it like this. Sorry, this should be X. Yeah, it's a submersion, exactly. So that's how you can kind of build your metric out of it in practice. There's some technical details, like this pi is obviously not invertible, well, this d pi is not invertible, right? But you can kind of look at horizontal and vertical spaces and things like that, but won't waste everyone's time trying to fumble around with what that is. But hopefully that helps.
I've got a question for you, James. I'll just imagine I'm just a clueless newbie. And you already answered this question, by the way, so you can just reiterate what you said before, but I think there's a possible danger that people might get confused. So if you scroll back up to where you did the quotient of Rn by Zn.
Yes.
I might, if I'm trying to understand this for the first time, I might put n equals 1 because, you know, 1's the smallest number I can pick. And then I might see that you said that S1 was flat, but I learned in my undergraduate calculus course that the curvature of S was 1 and not 0. So like I said, you already answered this question, but maybe you want to just talk about it for a few more seconds.
Yeah. So that's a good point. I guess there's kind of two different notions of curvature we're using here, right? So you can define the curvature of one-dimensional curves sitting in R2 or R3, or Rn, I guess. But Riemannian geometry in dimension 1 is pretty much trivial in the sense that the curvature, as we're going to define it, will vanish. So yes, so that's a good point. Just that these two notions of curvature are different, and we'll define it properly next time.
There's a little discussion in the chat. I think it just follows on from what you were saying. I don't know, Ramiro, you might want to, if you want to say something, you can.
No, not important. Just a remark. I mean, that you can, of course, there's a natural way of defining the distance, right? It's just the distance between orbits. But of course, if you want the Riemannian metric, then you need the smoothness, right? Although for an isometric group, actually, you always have a smooth quotient on an open dense subset, if you're willing to give away some bad orbits, singular ones. But yeah, just wanted to mention that the metric space interpretation of Wilhelm's question.
Cool.
Yeah, great stuff, James.
Yeah.
Thank you.
I don't know, Paul, when do we have a time limit? Any more questions?
We can stay as long as you have questions, Glenn.
No, I'm gonna not do any more role play, I think. No, I just thought that was just a thing I wanted people to be clear on, that's all.
Yeah, absolutely. Yeah. All right. That seems like we might have come to a pretty good place to stop there.
Oh, well, thanks everyone for having me again. Hopefully
we should thank you, James. You put in all the work to do this. We should thank James. Yeah. Okay. I'm going to thank you.
Thanks, James.
Yeah. Thank you very much. Yeah. Very nice.
Looking forward to curvature and connections next time.
That'd be fun.
We'll be asking about your intuition with the torsion, I think. I'll save that for next time.
There's a great Stack Exchange article, actually, but maybe I'll link it in the chat next time or something.
Yeah, I think that the issue with the torsion is that there are sometimes good reasons to expect it not to vanish. Anyway, we'll talk about it next time.
Well, James actually works with Hermitian geometry, right? So there's torsion everywhere.
Yeah.
Yeah, cool, great. Perfect speaker.
He's trying to make a living out of it. So it should not. So we meet again next week, right? Next week, same time?
Yeah.
Right. Yeah. Same time, same channel, whatever. Yeah.
Okay, thanks.
Okay. Yeah. Awesome.
See you next time.
Yeah. I guess I'll end the session now. Thanks so much, James. Very good.
Thank you. See you next week.
Yeah. See you next week. Cheers.